Okay, so what we want to do is talk about the derivative of a parametric. So let's say we've got let me just pick an arbitrary parametric. So let's say we have, it's defined as x of t and y of t, where, I don't know, x of t is equal to 2t plus 1, and y as a function of t is equal to, let's say, t squared. Okay. Now, what we can do is let's just graph this out again because this is good practice. So we've got t, we've got x as a function of t, and we've got y as a function of t. Let's also, and then we'll of course discuss x, y. Okay, and let's let t, I don't know, go from 0 to 2. Okay, something very basic. So t is 0, 1, and 2. Now t can take on the values in between these. Okay, but I'm just writing down the integer values here. So when I plug in 0, I get 0 for both these. Okay. When I plug in 1, x becomes 2 times 1 plus 1, which is 3. And y becomes just 1. And when I plug in 2, I get 2 times 2, which is 4, plus 1 is 5. And here I get 2 squared, which is 4. You know, another way to take a look, another way to think about this is we can, so let's, just before I do that, let's just graph all these points. So 0, 0. Okay, we've got to go over 1, 2, 3, 4, 5, 4, like that. So 3, 1, 1, 2, 3, up 1. And then 5 over 4 up. So like this. Okay. Now I don't put arrows here because it's not going any further. It stops at those. And our direction is headed that way. So if you were a little bug following this parametric, you would start here and you would go up to here. Just like that. Now another way that we can get the same graph is to go ahead and solve. I'll come up with a new function. Okay, I'm going to call this new function, I don't know, h of x. Okay. And so, well, so this is y. Okay. And notice that y, which is a function of t, is equal to t squared. Well, I can solve this for t. So x is equal to 2t plus 1. So x minus 1 is equal to 2t. So x minus 1 over 2 is equal to t. And if I plug that right into here, I end up with this guy squared. Like that. Okay. So if I square this, okay, I get the following. I'll get 1/4 times the quantity of x squared minus 2x plus 1. And if I distribute that in, I get x squared over 4 minus x over 2 plus 1/4. Okay, so this curve right here, if I graphed it out using this function, if I plug in 0, let's see here, this isn't right here. 0, 0 is not the point. Made an error, so let's go back. When I plug in 0 here, this guy ends up being 1. See, we found an error. So let's try that. So 1 over, that's where we start. Then 3, up 1, and then 5, just like this. There we go. Again, we're still moving along just like that. But here's where we start, and here's where we end. Okay, so there's our parametric curve. That looks better. So again, if you were to plug in values here, Okay, let's see here. Give me a second. So to get this point right here, if we were to plug in 1 for x, okay, I would get 1/4 minus a half plus 1/4. Okay, so if my x value is 1, I would get 1/4 minus 1/2 plus 1/4. So a fourth plus a fourth is a half, minus a half is 0. So that point's there. Let's try another point. Let's try when x is 3. When I plug in 3 into here, I get 9/4 minus 3/2 plus 1/4. So this is 10/4 minus 3/2, or 10/4 minus 6/4, which is 4/4, which is 1. So 3 over 1 up. Okay, so this describes the same curve. Now, I may want dy dx. Okay, now if I want dy dx, I can put it into this form right here, and I can differentiate this. So this is going to be 2x over 4, so it'll be x over 2. Derivative of this guy right here is still negative, and it'll just be negative 1/2, right? Okay. But let's say we wanted it directly from this right here. So let me erase this. Okay, let's say I want the derivative. I'd like dy dx directly from this information. Well, dy dx should be equal to, by the chain rule, it's going to be equal to dy dt, okay, times, hang on one second, let me just think about this. Yeah, I wrote that down wrong. Let's just erase this. So if we want, let's say dx dt, actually I'll go like this. I'll say y of t I don't like any of this. Okay, here I've got a good way of describing this. So let's say I want to take dt of y. Excuse me, I don't want ddt of y. I want dx ddx of y, which is a function of t. Okay, so you would see some t's floating around in here. Well, we would want to use the chain rule here. Okay, I'm going to say it like this. Let's say y is a function of x, so this guy right here, h of x. And now I want h prime of x, which is dy dx. Okay, that's what I'm looking for. Well, to find this, y is a function of t. Okay, so really I've got some t's going on in there. So what we have using the Leibniz notation, we've got dy dt is equal to dy dx times dx dt. That's our chain rule. And so if we go ahead and we move some stuff around here, if we want what is dy dx, that's equal to dy dt divided by, so dy dt divided by dx dt. And so you'll typically see this written like this: dy dx is equal to dy dt over dx dt, just like that. So let's go ahead and use that here. So if I want to go directly to find directly to this from this information, I say that dy dx is equal to dy dt. So derivative of this with respect to t is 2t. And then the derivative of x with respect to t is just 2. Okay. And so that reduces to just t. And t, in terms of x, t is equal to, now I'm going to go ahead and replace that with either of these two, but it's going to be best replaced with the x. We have that x is equal to 2t plus 1. So x minus 1 is equal to 2t. So t is equal to x minus 1 over 2, which is 1/2 x minus a half, which is this guy right here. So we've found dx dt. Excuse me, dy dx.